This module introduces you to two compartment models and how they differ from one compartment models. When you administer a drug to an animal and the resulting plasma drug concentration time profile seems to best fit to a one compartment model, this means that the drug distributes rapidly wherever it is destined to go in the body. In other words, distribution is essentially instantaneous, and the volume of distribution is a constant value that reflects the extent of the drug's distribution. Because we are measuring the drug's concentration in plasma, the decline for a one-compartment model is mono-exponential because there isn't a measurable distribution phase, or a phase where distribution contributes to the decline in drug concentrations. It is only elimination, a single process, that is contributing to the decline. In contrast, for drugs that exhibit two-compartment pharmacokinetics, distribution to some of the tissues takes some time. That is, it's not instantaneous. And as a result, the initial volume of distribution is quite small, but it gets larger as the drug distributes further. So here we have a schematic of the two-compartment model with its parameters. The K12 and the K21 are rate constants for the movement of the drug to and from the central to the peripheral compartments, and the K10, as in the one-compartment model, is the rate constant that relates the amount of drug in the central compartment to the amount of drug excreted per unit time. Now, because initially both distribution to the peripheral compartment and elimination are contributing to the declining drug concentrations that we are measuring in the central compartment, we see that for drugs exhibiting two-compartment pharmacokinetics, the initial portion of the plasma drug concentration time profile is steeper than the later portions. We need to describe this profile using more exponential terms, at least two in this case, so that we capture this difference between the initial and later portions of the curve. So all drugs actually have a distribution phase, but for some it's so rapid that we don't pick it up. Look, for example, at this time concentration curve for the aminoglycoside gentamicin. It does take a little time to distribute, but by the time we take the first plasma samples a few minutes after the dose was given, the distribution is complete, and we can describe the pharmacokinetics using a single constant volume of distribution and therefore a mono-exponential equation. In contrast, this drug, which is vancomycin, distributes more slowly. Notice the scale of the x-axis, it's hours. So the decline in concentration for the first few samples is much steeper than later because we still have a distribution process happening that contributes to that decline.